Hi everyone, welcome to the new module 2 of the three modules. So, in this module, we go inside the data encryption standard (DES). We'll examine its complete structure and understand exactly why it's 56-bit key inadequate, and see how attackers broke it. By the end, you'll understand both DES was a breakthrough in 1977 and why it became a liability by 1998. So, let's go. Let's start with the key facts. DES operates on a 64-bit data block. Data blocks. The bits are parity bits used for error checking. They carry no key information. This leaves 56 effective key bits. The cipher used 16 rounds. It was a standardized by NIST, uh, then called the National Bureau of Standards in 1977, and remained the dominant encryption standard for over 20 years. Keep the number 56 in mind. Everything in this module comes back to 56 bits. So, the overall structure of DES is straightforward. When a 64-bit plaintext block enters, the first step is an initial permutation. The 64 bits are shuffled according to a fixed table. This doesn't add a security, it's a hardware optimization for the original design era. Then 16 Fizzle run in a sequence, each using different 48-bit subkey. After all 16 rounds, final permutation, the inverse of the initial one, is applied to produce 64 bit ciphertext. The security of DS lives inside those 16 rounds, specifically inside the round of the function f. So let's start on the DS round. At the start of each round, we have 32-bit right half first. It expands from 32 to 48 bits by duplicating some bits. According to the expansion table, this expansion allows XOR with the line with the 48 bits. After XORing with the subkey, we pass the 48 result through a substitution box or S box. Each S box takes 6 bits and outputs 4 bits, compressing the 48 bits back down to 32. Then a fixed permutation shuffles those 32 bits to spread their influence. Finally, this 32-bit output is XORed with the left half to become the new right half. The old right half becomes the new left half. Repeat 15 more times. The S-box deserves special attention. They are the only nonlinear component in the S. Everything else, permutations, the XOR operations, the expansion, these are all linear transformations. A linear cipher would be trivially breakable using linear algebra. The S-box introduced the non-linearity that prevents this. Each S-box contains a 4-row, 16-column lookup table. The 6-bit input selects a row using the outermost 2 bits and a column using the inner 4 bits. The corresponding table value is the 4 bit. The actual table values for all 86 S-box in the DS were carefully designed. In fact, IBM knew in 1977 that the S-box design needed to resist differential cryptanalysis. Through this wasn't publicly disclosed until 1994. Where do the 16 round subkeys come from? The DES key schedule generates them all from the original 56-bit master key. First, a permutation called PC1 selects the rearranges the 56 bits into two 20-bit halves. Before each round, both halves are rotated left by one or two positions. The rotation amount varies by round. Then a second permutation, PC2, selected 48 of the 56 bits to form the round subkey. The rotation ensures that different bit positions contribute to different round subkeys, spreading the key material across all 16 rounds. Here is the story gets serious. 2 the power 2 to the power of 56 seems like a large number, about 72 quadrillion possible keys. In 1977, this was considered sufficient. An exhaustive search was estimated to take decades with available hardware, but computing power flows Moore's law. It roughly doubles every 18th month. By 1998, the Electronic Frontier Foundation built the dedicated DS cracking machine called Deep Cracker for 2,500 grand dollars and broke the DS. It tried, 19 billion keys per second and broke the DS in 56 hours. Let me repeat that. The entire security of a global encryption standard collapsed in under 3 days. By 2008, a network of ordinary internet-connected computers run by distributed .NET cracked DES in about 12 days. No specialized hardware needed. Today, using cloud GPU clusters that comes few dollars per hour, this can be broken in under 24 hours for around just a few hundreds dollars. The 56-bit key was catastrophically insufficient, and the critics said so in 1975 when DS was being standardized. Brute force isn't the only attack on DS. Two theoretically research uh, differential crypt analysis developed by Beham and Shamir in 1990 analyzes analyzes how differences in chosen plaintext pairs propagate through rounds. It can break DS with 2 with power 47 chosen plaintexts, less than brute force but still impractical. Linear crypt analysis, introduced by Matsui in 1993, approximates Xbox behavior with linear equations and needs 20 with power 43 uh, known plaintexts. Both attacks are theoretically important but practically moot since brute force became feasible first. Importantly, NSA document declassified in 1990 revealed that DES designers had been aware of differential cryptanalysis and designed the Xbox to resist it, but kept this secret. When DES weakness became undeniable, the industry adopted that DS as stopgap. 3DS applies DS three times using the pattern encrypt, decrypt, encrypt, or EDE, with three keys using the three independent 56 bit keys. Gives an effective key length of 16.8 bits, far beyond the brute force, but 3DS has serious problems. It's three times slower than DS, and its a 64 bits block makes makes it vulnerable to the Sweet 32 birthday attack, when encrypting large volumes of data, roughly 32 gigabytes or more, with the same key. NIST officially decrypts 3D in 2023. It was always temporary solution, and EES it's a permanent replacement. For lessons from the EES, first, design key length for the future, not the present. Second, public cryptographic security it's a feature, not a vulnerability. Third, small block size create birthday attack risks at scale. Fourth, no algorithm is eternal. Even EAS will eventually need successor. In Module 3, we met the successor EAS.